15. Let Fg belong to L1 of Rn. Then F star G is well defined and norm F star G in 1 is less than or equal to norm F1 norm G1. So this is Young's inequality when P equals 1. We have already done when it is P. So this is easier in fact. Okay, so solution. So we look at the following integral of Rn with respect to x, integral Rn, with respect to y, mod Fy g of x minus y dy dx. So this is again, everything is non-negative in the integrand, so you can interchange the order of integration. So this is Rn of y of mod Fy integral Rn x mod g of x minus y dx dy. Okay, so y is a constant as far as the inner integral is concerned, and g of x minus y is just a translate of g, and therefore by the translation invariance of Lebesgue measure, this is in fact equal to norm g1. Okay, so this is equal to norm g1. It's a constant, it will come out integral Rn mod Fy dy, and therefore that's equal to norm g1 norm f1, and that is given to be finite. So with the absolute value, this is integrable. Therefore by Fubini's theorem, for almost every x going to integral Rn of f of y g of x minus y dy exists, and therefore for almost every x, so f star g of x equals integral Rn f of y g of x minus y dy is defined almost everywhere, and of course mod f star g of x is precisely less than or equal to this quantity here, and therefore you have norm of f star g1 is less than or equal to norm g1 into norm f1. Okay, so that completes that exercise. So this is much easier than the case for when one of the functions is in LP. Okay, so now 16. Let A be contained in R finite interval. Let 1 less than or equal to P, 1 strictly less than P less than or equal to infinity, and Fn bounded sequence in LP of AB. Then show that 1 less than P less than infinity, Fn weakly converges to F in LP if and only if integral A to B Fn phi converges to integral A to B F phi dx of course for all phi in CC AB. And then secondly, P equals infinity. So Fn converges to F weak star in LP, L infinity AB, if and only if integral AB Fn phi dx converges to integral A to B F phi dx for all phi in CC of AB. Okay, solution. So let's look at 1 less than P less than infinity. Okay, so let us assume that Fn converges weakly to F in LP. So this implies for every phi in L P star AB, you have integral Fn phi converges to integral F phi AB dx AB dx. Okay, and in particular, every continuous function with compact support CC of AB is contained in LP star AB. It's in any LP space, and therefore in particular you have that for every phi this happens. Okay, so okay, and conversely, so let integral Fn phi dx AB converge to integral A to B F phi dx for every phi in CC of AB. Okay, so then given any G in LP star AB, there exists phi in CC of AB. Because 1 is less than P less than infinity, so is P star. So everything CC is always dense in all these spaces, such that norm G minus phi P star is less than epsilon. Okay, so then integral Fng minus dx minus integral Fg dx, always between A and B, okay, is equal to integral Fn of G minus phi dx from A to B plus integral A to B Fn phi dx minus integral A to B F phi dx plus integral A to B F of phi minus G dx. Okay, so now we take the modulus of this, so that is less than or equal to modulus of this plus modulus here, and then finally modulus here. Okay, so Fn is given to me bounded sequence in LP. Okay, so this is less than or equal to norm Fn in LP, norm G minus phi in P star by the Helder inequality, plus mod integral A to B Fn phi dx minus integral A to B F phi dx, plus mod norm Fp norm phi minus G in P star. Okay, so norm Fnp is bounded, so this is less than m times epsilon, plus mod integral A to B Fn phi minus integral dx minus integral A to B F phi dx, okay, plus norm Fp times epsilon. Okay, and you are given that this goes to 0, and therefore everything can be made arbitrarily small. So this implies that integral A to B Fng dx goes to integral A to B Fg dx for every G in LP star AB, and that is Fn goes to F weakly in LP. Okay, so that proves 1. For 2, P equals infinity, so P star equal to 1, and again you have CC of AB is dense in L1. Okay, so same proof as above, and therefore gives integral Fn phi g AB dx goes to integral A to B Fg dx for all g in L1 of AB. Okay, recall that L1 star is L infinity, and therefore if you are doing this Fn is in L infinity now a sequence, and if this happens in the pre-dual space, then this implies that Fn goes to F in weak star. So this is the characterization we had, and therefore we have this. Okay, 17. Okay, let F be from C01 to R continuous and F0 equals F1. So it's a periodic function. Define Fnx equals f of nx x in 0 1 1 by n. So you are rescaling the same function. So I have a function f which is say something like this. The n values need not be 0. I am just for the sake of the picture, this is 0 1. So now we are taking 0 1 by n and then reproducing the same function. 1 by n going to 0 1 is given by x going to nx. Okay, so using that mapping of 0 1 by n to 0 1, we are redefining this mapping. So this, and then you extend it periodically to k minus 1 by n, k by n, 2 less than equal to k less than equal to n. So what are we doing here? So we are taking 0 1 and dividing it into n equal parts. So this is 1 by n, this is 2 by n, this is k minus 1 by n, this is k by n, and so on. This is n minus 1 by n, and then 1 is n by n, of course. Okay, so from 2, so what you did earlier, so you took this function f which is on 0 1 and then you scaled it to 0 1. Now you reproduce the same function like this. Okay, so after scaling you simply move that function like this. Okay, so let m equals integral 0 to 1 f of t dt, which of course will be finite because f is a continuous function. Okay, so then define gt equals m for all t in 0 1. Then Fn is of course in all the LP spaces. It's in L infinity and it's in all the LP spaces because it's a continuous function on a compact set, and therefore that's why we took periodic. Okay, so because when we take the same value at the endpoints and then you repeat, then it becomes a continuous function. So f is a continuous function on a compact set, therefore it is in all the LP spaces, and therefore you have Fn weakly converges to G in LP 0 1, 1 less than p less than infinity, and Fn weak star converges to G in LP 0 1 if in L infinity 0. Okay, so this is this function which we have scaled and reproduced converges in LP or either weakly or in weak star to the average value, because this integral ft dt is nothing but the integral of f divided by length of the interval is 1. So this is nothing but the mean value or average value of the function in this. So this periodic scaling and periodic repetition, if you do, then that sequence converges to the average value of f. So that is in the weak or weak star topology, depending on the space. So solution. So by exercise 16, enough to show that for all phi in CC of 0, 1, you have integral 0 to 1 fn phi dx converges to integral g f g dx, that is 0 to 1, and g is equal to m, so that is m times integral 0 to 1 f dx. Sorry. No, that's not what I meant. It converges to g phi dx, and that is equal to m times phi dx. Okay, so this is what we have to show. The fn converges to g weakly, that is what the assertion was, not f. So, and g is m, so this is what we must show. So, okay, so let us compute this integral. So, integral 0 to 1 fn phi dx. That I am going to split into the various intervals. So, k equals 1 to n, okay, integral k minus 1 by n to k by n of fn t phi t dt. And that let me write as sigma k equals 1 to n integral k minus 1 by n to k by n fn t and phi t minus phi k minus 1 by n dt. Okay, so I am just subtracting the base value of phi, okay, plus sigma k equals 1 to n of phi of k minus 1 by n into integral k minus 1 by n k by n fn t dt. Okay. Now, phi is continuous with compact support. Therefore, it is uniformly continuous. Therefore, given epsilon greater than 0, there exists a delta greater than 0 such that if 1 by n is less than delta, we have mod phi t minus phi k minus 1 by n is less than epsilon for all t in k minus 1 by n, k by n. Because if t belongs to this interval, t minus k minus 1 by n will be less than the length of this interval, which is 1 by n, which is less than delta, and therefore phi t minus phi k minus 1 by n is less than epsilon. And also you have that norm f infinity is less than or equal to some m, say some this thing. So let us look at the first term. So modulus of sigma k equals 1 to n integral k minus 1 by n to k by n fn t phi t minus phi k minus 1 by n dt. Okay, modulus of this is less than or equal to this, when I take the modulus inside, this is less than epsilon times integral sigma mod fn from k minus 1 to k. Okay, and then that's integral 0 to 1 fn t mod dt. But fn is less than or equal to m because it is just f which is repeated and rescaled and repeated. So this is less than or equal to epsilon times m. Okay. So that is fixed. Okay. So that is the first term. So now let us look at the second term, which is sigma k equals. So let us look at one such integral in that term. So integral k minus 1 by n to k by n fn t dt. Okay. So this is nothing but, because we have just repeated the function again and again, so this integral on any such interval is nothing but the integral on 0 to 1 by n f of nx dx. And that, if I make a change of variable, this is nothing but 1 by n integral 0 to 1. So I put nx equals t, so dx is dt by n, and therefore I get a dt by n, and then this becomes f of t, and 1 by n becomes 1. Okay, so this is 1 by n integral 0 to 1 f of t, and this is nothing but m by n. M is the value of the integral of f, and therefore that's equal to n. So this is what you get from this for every k. Okay, so this is for every k, and therefore you get that integral 0. So second term, what is the second term? Sigma k equals 1 to n phi of k minus 1 by n integral k minus 1 by n to k by n integral k minus 1 by n to k by n fn t dt. So that we just computed. So this is equal to m times sigma m by n sigma k equals 1 to n phi of k minus 1 by n. Now as n tends to infinity, what does this? So as n tends to infinity, the 1 by n sigma k minus 1 by n f of phi of k minus 1 by n is nothing but the Riemann sum. 1 by n are the lengths of each of these intervals, where I am taking the value of the lowest point, and phi is a continuous function, so for any point it should converge. So this should converge to m times integral 0 to 1 phi of x dx. Okay, so that is exactly what we want. So what did we show? We have shown that integral fn phi, so for every phi in cc of 0 1, we have shown that integral 0 to 1 fn phi dx converges. So this first term goes to 0 because it's arbitrarily small, it's less than epsilon m. So the second term converges to m times, so m times integral 0 to 1 phi of x phi dx. Okay, and that's precisely what we wanted to show, and that is fn goes weakly to f in LP 0 1, 1 less than p less than infinity, and it goes to weak star, sorry, g in L infinity 0 1, where g is identically equal to m, which is integral 0 to 1 f of x dx. Okay, so that is that. So we will wind up with this and start the next new chapter next time.